So we are going to talk about parallelism in merge sort of parallel algorithm. Parallel merge sort is basically an upgrade version of the normal merge sort, but it's designed to work more faster by using multiply procedure. The way it's worked is quite simple. First, it keeps breaking to the list into smaller parts until each part has just one item. Then it starts sorting those parts at the same time using different processors. Once everything is sorted, it's combined them back together towards the final sorted list. The beauty of this algorithm is how it's used parallelism, because each small part can be handled independently. Everything can be done faster instead of waiting one by one like in the usual method.
Let's move on to task decomposition and distribution in parallel merge sort. In parallel merge sort, the algorithm first breaks the input list into smaller sublists through recursive splitting. These sublists are then distributed to different processes, allowing them to be sorted at the same time. Once sorting is done, the merging process is also done in parallel step by step. This makes the whole process much faster because the workload is shared and done simultaneously instead of one after another.
So next is analysis of the parallel merge sort using words and span. When we talk about words in a parallel algorithm, we need the total amount of the efforts or operators it takes to finish the job. For parallel merge sort, the word is on lock, which is the same as the regular versions. But what makes parallel algorithms special is the span. That's the longest batch of steps that have to be done in order and can be split up. For this algorithm, the span is overlocked too, because even though a lot of tasks can be done at the same time, some steps, especially the merging part, still depends on others done first. The span is what sets the limit on how fast the algorithm can run, no matter how many processors we.
The scenario that we use for work and span calculation is 8 elements of data and 4 processes. We need to use the equation Wn equal to big O multiply n log n, where n is the number of data that we have from this calculation. We get 8 multiplied by 3, which is 24 operations. As for span, we use the formula in the slide and let n equal to 8. And from this, we will get 27 time unit. From the answers, we can calculate the average available parallelism using the equation Wn over Sn, which equal to 0.89.
For the diagram analysis, I choose the diagram with 8 data. The first half is the divide, which is when the data are divided into small portions, while the other half is conquer, where the data will be sorted by ascending or descending order. In this case, we use the ascending order to sort through the data using merge sort. Understanding Amdahl's law and algorithm speedup. Amdahl's law helps us understand the limit of speedup when using parallel processing. It shows that even if we use many processes, the parts of the algorithm that can't be parallelized will limit the overall speed. For example, if 20% of a task must run in the serial, the maximum speedup is only 5 times faster, no matter how many CPUs we use. So improving the serial part is just as important as parallelizing the rest.
In this slide, I will explain how the span or critical path limits the speedup we can achieve in parallel algorithms. The span refers to the longest change of tasks that must be done one after another. Without any parallel execution, these tasks depend on each other, so they can't run at the same time. Even if we have a large amount of total work that can be done in parallel, the span still sets a limit on how fast the whole task can be completed. For example, imagine we have 10,000 total operations. That sounds like a lot, and we might think adding more processes will keep making it faster. But if the span is 100 steps, then the best possible speedup is only 100 times faster, no matter how many processes we use. So the critical path becomes the bottleneck that limits performance in parallel computing.
For the theoretical speedup calculation, we assume that if 10% of the operations are sequential with infinite processes, the speed can be calculated using this equation, where f is the percentage. From this, we get the maximum speedup equal to 10. As for practical speedup, we assume that we have 15% synchronization overhead, which will make the actual speedup be 1.58 when calculated using that formula. Some factors need to be considered when discussing about a framework. First, cache coherency overhead, because the system must ensure all cores have the most up-to-date data. Second, false sharing, as it can lead to unnecessary cache invalidation and slowdowns. Third is NUMA effects, which will result in higher latency. These factors can significantly impact the practical performance, efficiency, and scalability of parallel algorithm beyond what is predicted by theoretical analysis alone.
Now, we'll look on the reflection on how work, span, and critical path inform parallel algorithm optimization. When designing parallel algorithms, it's essential to understand the 3 core ideas, which is work, where it refers to the total amount of computation performed by the algorithm. It tells us how much effort is needed overall and helps prevent overloading the system with unnecessary steps. The next is span, which is also known as the critical part. It is the longest chain of dependent tasks that must be completed in sequence. It represents the theoretical limit on how fast the algorithm can run, no matter how many processors are used. And together, work and span give us insight into the algorithm's parallel performance. For instance, if the span is long, even with many processors, the execution time won't improve much. But if the work is too large, resources may be wasted, even if speed improves. And to optimize, we aim to reduce the span to improve speed, and we also keep the work efficient to avoid unnecessary overhead.
For trade-off between achieving high parallelism and dealing with communications and synchronization overhead, there are a few pros and cons that are bound to happen. One of the advantages is faster sorting because of the usage of multiple processes. Next, high parallelism can also encourage big data handling because of the large amount of data sets that can be used at the same time. High parallelization can also have a few disadvantages. For example, communication overhead, because the processes tend to slow down when there are too many data that needs to be moved and merged. Meanwhile, synchronization overhead can happen when all processors need to access the same resource, which then causes a bottleneck.